Good afternoon, everyone. My name is Monica, working as assistant professor in CSE AIML department at G. Pullareddy Engineering College, Kurnool. So today I would like to discuss on the topic that is quantum bits and circuits. So bits, gates, and circuits, these are nothing but they are also called as building blocks of quantum computing. So bits are nothing but they are the qubits. So qubits means which include 0, 1 or both. So gates means which are the quantum gates. So quantum gates are nothing but like we use here Pauli X gate, T naught gate, Hadamard gate, CC naught gate. So these are the quantum gates. And circuits are nothing but these are the sequence of operations sequence of operations. Okay, so bits are nothing but the quantum bits which are 0, 1 or both, and the quantum gates, the Pauli X gate, Z gate, Hadamard gate, Z gate, Hadamard gate, C naught gate, and also the CC naught gate. So circuits, so all the sequence of operations which are included by using the quantum gates and also the measurements, which are then we can build a quantum circuit. So here we will understand about single qubit gates, the block sphere, next superposition, and also about the measurement. So in this video we'll understand about single qubit gate, the block sphere, superposition, and also about the measurement we'll understand here. So the quantum bits, gates and circuits, they act like the building blocks of the quantum circuit. So if at all we consider the classic computers, if, first of all we have to understand about the concept of half adder. So half adder is nothing but which is designed to add single bit numbers, single bit numbers, that is 0 or 1. Okay, so it has two inputs and two outputs. Okay, so if at all we see the diagram, that is this is the half adder. We have two inputs, that is A and B. These are the inputs here, and the output for the half adder will be sum and carry. This is represented with S and this is represented with C. So totally we are having two inputs, that is A and B, and as we are giving two inputs, we have to get two outputs also. So inputs are A and B, and outputs are the sum and carry. So now we have to understand the truth table for this inputs. So write down the inputs, that is A, B, write down the outputs, that is sum and carry. So which focuses this half adder concept, it is used to add the single bit numbers only, that is 0 or 1 only. So the inputs will be 0, 0, 0, 1, 1, 0 and also 1, 1. So for 0 and 0, the sum is 0, the carry, there is no carry, so it is 0. For 0, 1, the sum is 1 and that is 0, 0. For 1, 0, it is 1 and 0. For 1, 1, it is 0 and 1. So this is nothing but this is the truth table. So A, B are the inputs, these are the inputs here, and sum and carry are the outputs. So this is the diagram for the, sorry, this is the truth table for the half adder. So next, based on this truth table, we have to write down, we have to draw the K map. So K map for the sum and also for the carry. So first, draw the K map for sum and next the K map for carry. So we are having two inputs, that is 0 and 1, and AB are the inputs here. This is 0 and 1. So we have to look for only for the sum. So in the sum, here we are getting 1 and at this input also we are getting the 1. So input is 0 and for B input 1 we are getting 1. So map with 0 and 1, this is 1 here. Next one is 1 0. 1 0, here it is mapped. So as we are focusing on the sum, where the sum is 1, we have to map with that. So this can be written as A bar B and this can be written as A B bar. So 0 means it is complement. So 1 means we can write down in the same way. So this can be written as A bar B XOR A B bar. So this is the expression for sum. For carry, again draw the K map. That is, we have the two inputs, that is A and B, 0 1 input and 0 and 1 input. For carry, now we have to look where the output is 1 actually. So 1 we are getting with A input as 1 and B input as 1. A is 1 and B is 1. A is 1 here and B is 1 here. So here we are mapping that one. And this can be written as AB. So 0 is not there, so we are not writing any complement, and this is the expression for the K map for carry. Now draw the logic diagram for sum. So we are having the inputs A and B. We are considering two inputs. So that is the reason we are using A and B here. We also have complements, that is A bar and also the B bar, and they are represented with the NOT gates like this. Okay, so these are the NOT gates here. These are the NOT gates. So now map for sum, that is A bar B. A bar, and this is, draw the gate, A B bar, A and B bar. This is the gate here. So this is the sum and this is output Y. So in this way we can draw the logic diagram for sum. In the same way we can also draw the logic diagram for the carry also. So for carry we are having only A and B. So input, that is A and B. You can also draw, actually A bar is not there, but still we are writing, this is A bar and this is B bar. And the logic diagram for carry is from A, and this is B, and draw the gate, and this is the Y for the carry. Okay, so in this way we are drawing the circuits. In classical and quantum circuits, the inputs are on the left and the outputs are on the right. So operations, they are usually represented by the symbols that are nothing but these are the, excuse me, operations are represented with symbols. So coming to the next topic, that is single qubit quantum gate. So qubit state, it is represented as a superposition, that 0 and also the 1 state. The quantum state, it is usually represented as the wave function is equal to alpha of 0 state plus beta of 1 state. So for 0, we know that the values are 1, 0. For 1, it is 0 and also the 1. Okay. So write down the wave function is equal to alpha of 1, 0 plus beta of 0 and 1 is nothing but alpha and beta. So the wave function is equal to alpha and also the beta. So these are nothing but these are called as the state vectors. So if we normalize this, we get alpha square beta square is equal to 1. So wave function is equal to the alpha and also the beta. And next one is about the Bloch sphere. So Bloch sphere, it is nothing but it is the 3D sphere. So it is used to visualize the state of a qubit. It is used to visualize the state of a qubit. So we know that classic bits are 0 or 1, and the qubit, that is 0 or 1, or it is both. Okay. And the mathematical representation, the qubit representation on Bloch sphere is wave function is equal to cos theta by 2, 0 state e power I pi sin theta by 2 is 1. So this is the qubit representation, visualizing qubit on the Bloch sphere. So where theta is nothing but it is the latitude, which represents 0 to 2 pi, and pi is the longitude, which represents 0 to, sorry, this is 0 to pi here, and this is 2 pi. Okay. So usually the North Pole is represented with 0 state, and the South Pole, it is represented with 1 state. And the equator, it is always in the superposition state. So this is about the Bloch sphere. So Bloch sphere is nothing but it is the 3D representation of the state of single qubit. So where we can represent the possible states of the qubit. So we know that a qubit only contains the 0 state and also the 1 state. That is 0 state or 1 state. So the wave function is equal to alpha of 0 plus beta of 1. So where alpha and beta, these are the complex numbers. So if we normalize that, alpha square plus beta square is equal to 1. So this is the normalization function. Okay. So a Bloch sphere, it contains the North Pole, the South Pole, and also the equator. So for the North Pole, it is always the state 0. For the South Pole, it is always 1. And for the equator, it lies in the superposition state. So next is using different gates. How can we analyze the quantum state? So that is quantum state analysis with the x comma h comma z gates. So x h z, these are the fundamental part or the basic building blocks of designing and understanding a quantum system. So to analyze quantum circuits, we can use them in combination to build the circuits. So X, H and Z, these are the fundamental part or the main part for designing and understanding the quantum system. So first we'll understand with X gate. So this is what we call it as the Pauli X gate, or it is also called as the bit flip gate. So we take the identity matrix, that is so the bits will be flipped here. So 1 0 0 1, this is the identity matrix. When we apply the Pauli X gate, it becomes 1 becomes 0, 0 becomes 1, 0 1, and 1 is 0. So where the state 0 is converted to 1 and 1 is converted to the 0 state. So where the bits are flipped here. So that is what we call it as the Pauli X gate. So the next one is the Z gate. So Z gate is called as the Pauli Z, or it is called as the space flip gate. So the output is 0, 1, 0, 0 and -1. So the state 0 will be 0. The state 1 becomes -1. So 0 means it is same. 1 means it becomes -1 phase. And next one is about the H gate, that is Hadamard gate. H gate. So this H gate, it creates the superposition. For 0, it is represented as 1 by root 2 of 0 state plus 1 state. For 1, it is written as 1 by root 2 of 0 minus 1. So we can write it as H is equal to 1 by root 2 of 1, 1, 1 and -1. So this is about the Hadamard gate. So X is called as the bit flip, Z is called as the phase flip, and H, it creates the superposition. And the next one is about the measurement. So measurement, how actually we observe a quantum state. So when we measure the qubit, it collapses to either 0 or 1. So P of 0 is equal to the alpha square and P of 1 is equal to the beta square. So for measurement, we can also measure it as before measurement and after measurement. Before measurement, after measurement. So before measurement is that qubit can be anywhere on the Bloch sphere. Qubit can be anywhere on the Bloch sphere. That is for before measurement. After measurement, the quantum state, it becomes either 0 or 1, because the quantum state, it loses superposition. So it can't be in both the 0 and 1 state. It has to be either in the 0 or the 1 state. So like if at all we write the steps, so during measurement, the qubit is in superposition. So after the measurement, so this is before measurement, the qubit is in the superposition state. After measurement, the qubit, it collapses. And last one is the result. The result is that you get either 0 or 1. So this is what we call it as the measurement topic. So now we'll understand a simple program. So how to develop or how to build a circuit. So single qubit quantum circuit. So first is that we write it as QC is equal to quantum circuit of 1 QC dot draw of MPL. Okay. So 1 is nothing but, so this quantum circuit. So quantum circuit, it is a class in a Qiskit library to create quantum circuit. So 1 is nothing but which tells how many qubits we want in a circuit. And MPL is nothing but it is a matplot library. So draw is nothing but it is a function. So before this, first we need to write it as from Qiskit import quantum circuit. So Qiskit, it is the library which is, it is an open source software library which is developed by IBM. So the output is like this. Because we did not include any of the gates, so just we are writing it as 1. So which includes 1 qubit here. So now we will apply different gates like X gate and also the H gates. So now we will understand how to write the X gate and also the H gate. So the first line is that from Qiskit import quantum circuit, import quantum circuit, QC is equal to quantum circuit of 1 QC dot X of 0. So X of 0, it is nothing but this is the X gate. Next QC dot draw of MPL. So now we are applying X gate on qubit 0. So the output is represented as, this is the qubit and this is the X gate. So similarly, if we want to add H gate, so we can write it as QC dot H of 0. QC dot draw function. In the draw function, we will include MPL. So the output will be as Q, this is the H, that is Hadamard gate, and we will get the output like this. So we can also add X gate and also the H gate at the same time also. So like this we can write QC is equal to quantum circuit of 1, QC dot X of 0, QC dot H of 0, QC dot draw, output equal to PL. Okay. So as we mentioned, only one single qubit, we get it as Q. We included H gate, X gate, we also included H gate. So this will be the output. We can also add the same gates. Here we can also add again QC dot X of 0. The output will be single qubit, X gate. Again we are applying X gate and this is the output. So we can add more than 3 gates also. QC dot H of 0, QC dot X of 0, QC dot again H of 0, QC dot draw of PL. So this is one single qubit, H, Z, and also H again. Okay. So this is what we call it as the single qubit and the quantum circuit. So we can also write the same for the multiple qubit. So multiple qubit means we have written only for one qubit here. This is multi-qubit quantum circuit. So again, the first line is from Qiskit import quantum circuit. Here we can add 2. 2 means more than one, that is multiple itself. Okay. So here we can write it as QC dot H of 0. Again we can add H of 1 here. QC dot draw of output is equal to MPL. So we included 2 qubits. So that is 1 and this is 2. So on 0 we are applying H gate. On 1 we are applying H gate. So this is the output. So this is for the multi-qubit quantum circuit. So we can also again add measurement concept also here. So at that time we have to include the measure function. So the measure function is that at that time we have to include the parameters quantum circuit 2, 2. So 2, 2 is that one represents for the classic bit and the other represents for the quantum. So next we can add the different gates QC dot H of 1, QC dot, we are measuring, right? So use the measure function. So this is measures qubit 0, QC dot measure of 1, 1, which measures qubit 1. And last one is QC dot draw of output is equal to MPL. So here we are using the 2 qubits, right? So Q0, Q1 it is, which uses the H gate. Again on the first qubit we are also using again the H gate here. So we are using the measure function. So we'll get this particular symbol. This is for the measurement. Okay. So again for this also measurement, because in the code we have written it as 0, 0 and also the 1, 1. So this is represented to 0 and this is represented to 1, and both of them they are connected to the C0. So measure function we are writing it as twice. So that is the reason here 2 times the measuring function is done, and we are using the Hadamard gate twice on the qubit 0 and also for the qubit 1. Okay, so the output is represented in this way. So like this we can represent for the multi-qubit quantum circuit. Thank you.